Um, in today's tutorial, we will discuss about the convergence and divergence of the series. So we have multiple scenarios for the different kind of series. So you know that in order to find the convergence of series, we have the multiple tests. I can name few of them like geometric series test, nth term divergence test, then integral test, p-test. P-test is basically generalization of the integral test, and the basic comparison test, limit comparison test, ratio test, root test, and there are several others test. So we have to carefully identify that which test is applicable on what kind of this series. For instance, I have chosen this series. So basically, I have to find the convergence of this series. Uh, so, uh, of course, by looking at the first side, we can say that this is not the geometric series, and we cannot apply the geometric series test. So let's move on further to the integral test, P test. So this is the in the numerator there are some powers we cannot apply the P test directly. So there are the possibilities to solve this series and find the conversion of this series by the um, integral test or the basic comparison test. So I will, in this tutorial section, I will rather focus to discuss the convergence of series by the integral test. So let us start solution. So since in the integral test we have to transform this summation into the integral form, let's say from 3 to infinity, and this is the uh, in terms of this a and the sequence a n will written as the in terms of the f of x. So this is the rather than 1 upon x, this will be 1 upon x natural log of x square root of natural log of x whole squared and to the minus 1 times dx. So since this is not a trivial integral that we can directly integrate, so we have to substitute some values. So let us make the substitution. So the substitution says since this is a natural log of x and the derivative of the natural log of x is given over there 1 upon x, so we can say that u is equal to natural log of x and the derivative is of u is du is equal to 1 upon x and to the dx. So while making the substitution, these upper and lower limits are in terms of x. Once you transform in terms of u, so this is since this is the x is equal to 3, so you will simply substitute over here. So this will become the lower limit is equal to u is equal to natural log of 3 and upper is natural log of infinity, of course, infinity. So this is the in terms of u, this is natural log of 3, and this is the infinity as it, and this is the 1 upon x, and dx is the du whole divided by uh, u and square root of u squared minus 1 is this. Since this is the improper integral of the type 1, because we cannot directly evaluate the limit on infinity. So we will approach this infinity by some dummy variable b. This approaches to infinity, and this says from natural log of 3 to and this b. So this b is basically approaching to infinity by some limiting value, and this is the du by u divided u times u squared minus 1 as it. So let us make the integration. So basically the formula 1 upon u times square root of u squared minus 1 is the formula for the secant inverse. So this says secant in limit b approaches to infinity, secant inverse of u positive, all the values of positive, and this is the b, and this is the natural log of 3. And once you apply the upper and lower limit, this will become limit b tends to infinity, secant inverse of b. Since the value, all values are positive, we will just write this u, and in the place of u is b is here because of the upper limit, minus secant inverse of the lower limit natural log of 3 is this. And now this is the limit b tends to infinity, and the secant inverse of b is, of course, the undefined value, so we can transform is at as a cos inverse, and b can as a 1 upon b, right? So minus secant inverse natural log of 3 will comes out as, so only we make the difference in this step from here to here. So secant inverse of b is equivalent to the cos inverse of 1 upon b. So we can directly say that as b goes to infinity, so 1 over b, b, and this b goes to infinity, so this will become cos inverse of 0. So this is the cos inverse of 0 minus secant inverse of natural log of b is this. So cos inverse of 0 is clearly pi upon 2 minus secant inverse is of the natural log of 3 is this. So once you evaluate this value in the radian, you will find once you evaluate these values by the calculator, in the radians, you will have the 1.1439. Of course, it's approximately equivalent to. So this has some constant value. So once the integration has some constant value, this means that this series is convergence, or you can say that this series is convergent by the converges by the integral test. Converges by the integral test. Right? Hence, the series that is from 3 to, sorry, the sum n is starting from 3 to infinity, 1 upon n, natural log of n, and square root of natural log of square n minus 1 converges by the integral test. By the integral test. Right? So in the forthcoming question, I'm going to discuss a kind of a bit different scenario. So let us take a look on the question. I have chosen this question to find the convergence. So basically, this is the alternating series because there is an alternative minus 1 raised to power n plus 1. So whenever n is odd, so this means that we will have the even values whenever n is odd. So let's say n is equal to 1. So we will find the even values. This means that all the terms are positive. So that will be natural log of n divided by n. Let's say n is equal to 2. That is even number. So 2 plus 1, this will become odd. So whole power of odd will turns out to be a negative number. So this says will alternate between positive, negative with some the nth term, that is natural log of n divided by n. So basically we have to carefully look for the convergence of this series. So we have to find the convergence. So let us start the convergence test. The solution says uh, uh, we will apply the alternating series test. So for in the alternating series test, the -1 whole raised to power n plus 1 will act as a alternator. So we have only to consider this an, which is the an is equal to natural log of n divided by n. So there are the three conditions that must be fulfilled. So the first condition is all ans are positive. So in this case, the first all the ans, because n is larger than equal to 1. So all the values of uh, n's are positive when you apply the in the natural log of n divided by n. So this will remain positive. So the first condition is satisfied that all ans are positive. The second condition is the sequence uh, must have the decreasing pattern. So in terms of decreasing pattern, we can say that an must be larger than equal to an plus 1. So in order to find the decreasing pattern, we can say that this an we can write in terms of f of x as a natural log of x divided by x. So we will take the first derivative f dash of x is equal to 1 minus natural log of x divided by x squared and x squared, and that is less than 0 for any values of x. So when not sorry, for any values of x whenever x is larger than epsilon. So when substitute f dash of x is equal to 0, you will see the value x is larger than epsilon. So this will remain positive. This says that f of x is decreasing. So the second condition is also satisfied that uh, because of this negative sign, because this is less than 0, so whenever the first derivative sign is less than 0, this means that the series is decreasing. For the third condition, you have to check that uh, uh, the limit of this an must goes to 0. So for this, let us recall. So this means that second condition is true and also satisfied, or you can say satisfied. Second condition is satisfied. So we can say that f dash of x is increasing. So this means an is much larger than an plus 1. So this is true, and the all ans are here. The first condition was also true. So now let us take third condition. In the third condition, limit n tends to infinity of the an. So this says that the limit n tends to infinity, natural log of n divided by n. So basically, if we directly apply the limit natural log of infinity by infinity, this is indeterminate form. So we will apply the L'Hopital rule, limit n tends to infinity. So natural log of n derivative is 1 upon n, and the derivative of n is 1. So 1 upon n, and n goes to infinity. So this whole goes to 0, and 0 divided by 1 is equal to 0. So this means that the limit n tends to infinity, an is equal to 0. So the third condition is also satisfied. Third condition also satisfied. So we have proven that all the three conditions of the alternating series alternating series test are satisfied. So therefore, we can say that the series converges. So here I will write formally that hence all three conditions, all three conditions of alternating series test are satisfied. Therefore, series converges. Hence, the series converges. So here in this phase, we have applied the alternating series test, and we have found that our series is convergent. So I have chosen another question uh, where we can check the convergence of the series. I have chosen this question. So first of all, we have to check that uh, which method we can apply. So basically here, I want to check the conditional convergence of the series. So the conditional convergence means uh, if I check the normal convergence, so for that the series is convergent. But if I check the absolute convergence, the series will diverges. So this is kind of series are called the conditionally convergent series. So let us start the work on this series. We have the series cos n pi divided by n, and this n summation is from 1 to infinity. So let us write this cos of n pi, because the cos of n pi is the alternating between +1 and to the -1. So we can write like -1 raised to power n. So this cos of n pi has reduced into the -1 raised to power n, because this can be positive 1, this can be negative 1 for the different values of n. Whenever n is even, so this will give the positive value like +1. Whenever n is odd number, this will give the negative value. So thus we can write our series as the sum n is starting from 1 to infinity cos n pi divided by n is equal to the sum n is starting from 1 to infinity, and this is the -1 raised to power n divided by n. So this cos of n pi has been replaced by the -1 raised to power n. So, and this is this series because of this alternator. This is the convergent alternating harmonic series. So here in this series, if we apply the same alternating series test that we have applied recently in the previous question, so if we apply the alternating series test, this series will convergent by the alternating series test. We can say that let say a n is equal to 1 upon n. So the first condition was all a n's are positive. So the a n's are positive, which is true. The second condition was the A, and this must has the decreasing pattern. So decreasing pattern mean, so the next term would be the small term. So we can say that an is larger than an plus 1, right? So if we have such kind of series, 1 upon n is larger than equal to 1 upon n plus 1. So of course, this series is larger. So this has the decreasing pattern. So this is true. Second condition is also satisfied. The third condition is if we apply the limit n goes to infinity of the an, and this is the limit n goes to infinity 1 upon n, and this goes to 0. So the third condition is also satisfied, that was saying that an must goes to 0. So this renders to the first condition, this is for the second condition, and this is for the third condition. All the three conditions are satisfied. Hence, the series converges by the alternating series test, because this series is the alternating harmonic series. But what if we apply the absolute convergence? Let us take the sum, this one. The sum n is starting from 1 to infinity minus 1 raised to power n divided by n. So let us take the mod. So once we take the mod, this term minus 1 raised to power n mod, for any value of n, this is positive 1, because either n is positive, so n is even, or n is odd. For even values, we are not in the trouble because we have just the positive values. For the negative values, whenever n is odd, so we have the negative ones. So these mod will make it always positive. So altogether, we will have the values like n is starting from 1 to infinity, and this is 1 upon n, right? This. Now we can apply the p-test. By the p-test, the power of p is equal to 1. So hence the series, hence by p-test, because the value of p is equal to 1, the series is diverges. The series diverges. So altogether, this series, I will write with the red color. Hence, therefore, you can say therefore, the series, the sum n is starting from 1 to infinity cos of n pi divided by n is conditionally convergent. Is conditionally convergent. Because of that, the normally without the absolute, the series was converges, like here. The series was converges. But whenever we applied the absolute convergence, the series diverges by the p-test. So the same series is convergent, and the same convergent series when we find the absolute convergence of the convergent series, that is divergent. So these kind of series are called the conditionally convergent series, right? So I gave you the wide spectrum of the uh, series. I started from the simple series, that is, I have applied the integral test. Then I have moved to the alternating series test. So I just hold the alternative minus 1 raised to power n plus 1 for a while time being, and then I applied the alternating series test. I have satisfied all the three conditions of the alternating series test. So the series was convergent. Now in that case, cos of n pi, so I have technically checked the both aspects of the convergence of the by the alternating series test, as well as to the um, um, applying the absolute values. For the absolutely, the series was divergent, but the normal series is convergent. So these kind of series are called the conditionally convergent series. Now, in the next question, uh, I will take the look on the uh, convergence of the power series. So the convergence of the power series basically renders to the uh, different things. So in the convergence of the power series, we have to look for the radius of convergence, interval of convergence, and we also check on the endpoint for either on the endpoints the series is convergent or divergent, and also we have to check on those endpoints, either on those points the series is absolutely convergent or the conditionally convergent. So let us start from here. So look, we have this series. That's the question. Just because of these x that are making it the power series. So the convergence of the power series can easily determined by the uh, ratio test. So the ratio test says that limit n tends to infinity, an plus 1 divided by an. That mod, since we have to look for the convergence, that must be less than 1. So we have the an. An is coming from this n plus 1 2x plus 1, this is x, whole power n, and 2n plus 1 and 2 power n. Whereas the an plus 1, because we have to identify those two terms, an plus 1. An is already given in the series, and an plus 1 we just increase the index. So this will become n plus 2 and 2x plus 1 whole power n plus 1 divided by 2n plus 3 and 2 power n plus 1. So let us use this equation, let me call equation star. So by equation star, this gives the limit n goes to infinity mod. I will just write the an plus 1 divided by an. So after rearranging the terms, so they can be written as n plus 2 divided by 2n plus 3 and 2x plus 1 whole power n plus 1 divided by 2 power n plus 1 times divided by the other term of the an, that is the 2n plus 1 divided by n plus 1 2 power n divided by 2x plus 1 whole raised to power n, and that is the mod, and that is less than 1. So this is in the numerator and this is in the denominator. The both are the same basis and the powers will add up. So n plus 1 minus n, so n and n will cancel out. So and the 2x plus 1 and this 2n, and with this will cancel, and this n with this n will cancel out. So 2n plus, so the one can say that 2x plus 1 whole divided by 2, and this has always a positive values, and the limit n goes to infinity. Thus, it says that the remaining terms are n plus 2 divided by 2n plus 3, n plus 2 divided by 2n plus 3 times the 2n plus 1 divided by n plus 1. So 2n plus 1 divided by n plus 1. That must be less than 1. So since the x is for all the positive values, so 2x plus 1 mod divided by 2, the limit n goes to infinity. So here I just to take the n common, n plus 1 plus 2 upon n, and here I will take the common n, 2 plus 3 upon n times also from here 2 plus 1 upon n divided by n 1 plus 1 upon n. This mod which is less than 1. So as limit n goes to infinity, so this 2 by n. So as this n goes to infinity, so the something goes to infinity something divided by infinity goes to 0. So this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So, and this is away. And the remaining one would be 1 by 2 times 2. So this term, this, and this. So we can say that 2x plus 1, 2x plus 1 mod divided by 2. And this is the 1 by 2 times 2. So this is the way, and this is less than 1. So altogether 2x plus 1 mod less divided by 2 and to the 1, which is less than 1. So we have the 2x plus 1 mod, which is less than 2. So once we open the mod, we will receive the value minus 2 less than 2x plus 1 less than 2. So once we get this free from any coefficients and the additives, so we have the minus 2, sorry, minus 3, minus 2, and minus 1 is minus 3, less than 2x, and less than 1. So 2 minus 1 is 1. So this goes minus 3 by 2 less than x and less than 1 upon 2. So this is these are the interval of convergence. So basically we have to check on these endpoints. At the moment I have not placed the equality sign. I'm not saying that the x is larger than equal to minus 3 by 2 and less than equal to 1 by 2, because I have to check on the endpoints. So basically the interval is this minus 3 by 2 and to the 1 by 2. So this is the interval of convergence. Within the interval, the series is convergent, but I'm looking at the endpoints at this point and at this point. So for this, for this, uh, just the just to put the value like this, and so we'll start from here. So we have the value of x is between minus 3 by 2 to the 1 by 2. So let us identify the cases. Case 1, when x is equal to minus 3 by 2. So whenever x, I'm looking at the endpoints, when x is equal to minus 3 by 2, I will put this x value into the our main series. So let me call this is the equation number capital A, equation A. So we will say that when x is equal to minus 3 by 2, equation A yields as the sum n is starting from 1 to infinity, n plus 1 divided by 2n plus 1, and after substituting the x equal to minus 3 by 2, so 2 times 2 multiplied by minus 3 by 2, 2 and uh, 2 will cancel out, and minus 3 and to the plus 1 would become minus 2 whole raised to power n divided by 2 raised to power n. So this is simply uh, uh, can be written as the sum n is starting from 1 to infinity, n plus 1 divided by 2n plus 1, and the this is written as minus 1 whole raised to power n, and 2 raised to power n, and 2 raised to power n. So they both are gone. So we are again in the regime of the alternating series. So because of this alternator. So I just have extract the minus 1 raised to power n from here, and the 2 raised to power n is separate out, and in the denominator we already had the 2 raised to power n. They both will cancel out. This is written as n is starting from 1 to infinity minus 1 raised to power n. And if I take the common n from here, 1 plus 1 upon n, and from here n is 2 plus 1 upon n is this way, and this can be written as the uh, limit as n goes to infinity. Or you can do one thing. At the moment, do not cancel it here, just to take the common. We'll cancel it at the later stages, n and n. So limit, and the power is minus 1 raised to power n. So n 1 plus 1 upon n, and the n 2 plus 1 upon n. So this is the way. This goes to 0 and this goes to 0. And the all the values minus 1 raised to power n, there are some because we are just looking at the we are applying the nth term divergence test. So this minus 1 will comes out as it, and the this limit says that this is the 1 upon 2. So the whole value is turns to the 1 upon 2, which is other than 0. So the nth term divergence test says that whatever the values you have intermediately, but if you look the nth term which is other than 0, this means that the series diverges by nth term divergence test. The series is divergent by the nth term divergence test. So at this endpoint minus 3 by 2, the series is divergent. So let us check at the point x is equal to 1 by 2. So whenever x is equal to 1 by 2, let us call as a case 2. Case 2. So when x is equal to 1 upon 2, then equation A implies. So we'll substitute x equal to 1 by 2 into the equation number A. So equation A is plus 1. So n plus 1 divided by 2n plus 1 into 2n will remain as it. At the place of x, we will substitute x equal to 1 by 2. So 2 times 1 by 2 is 1 plus 1. This is 2 raised to power n. So this will become like we have the sum n is starting from 1 to infinity, n plus 1 divided by 2n plus 1 times 2n and to the 2n, because that was the term was 2x plus 1. X is the 1 upon 2. So 2 and 2 cancel out, and the 1 plus 1 is 2 raised to power n. So the whole will cancel out basically over here. So the remaining term is the sum n is starting from 1 to infinity, n plus 1 and to the 2n plus 1. So here we will apply the same as we have applied in the previous case, which was case 1, nth term divergence test. The nth term divergence test says that the limit n goes to infinity. So n took the common 1 by n divided by n 2 plus 1 upon n, and this is the way. And once we apply the limit, this goes to 0, this goes to 0, and the remaining one is the 1 upon 2, which is other than 0. So the nth term divergence test says that once we apply the limit on the nth term and the answer is other than 0, that means that the series is divergent. So we can say that this series, whenever this series is also divergent, the series is divergent by n-term divergence test. So we can say that we have the interval this minus 3 by 2 to 1 by 2. Within the interval, the series is convergent, but at the endpoints, which is minus 3 by 2 and plus 1 by 2, so series is diverges. So the interval of convergence are, I can write the interval of convergence. Now I will illustrate all the values one by one. So let us just finishing the linings. So interval of convergence. So the interval of convergence are minus 3 by 2, less than x, and less than 1 by 2. So suppose that if the series is convergent on the endpoints, then we say that we can say that we have to apply this equality sign. This means that the series is also convergent on the endpoints. But in our case, the series was divergent on the endpoint, so we don't need to write these equality signs. So this, whenever you write in this form, this automatically means that the series is only convergent within the interval, but not on the endpoints. Right? So this was the first part of the question, where we had to look the convergence of the interval of convergence of the series. So look at the question. Find the series radius and interval of convergence. We have computed the interval of convergence. Now we have to look for the radius of convergence. How we can compute the radius of the convergence. Uh, we have started our working from here and we moved until here. So in the last we have reached at this point 2x plus 1 mod less than 2. So by solving this we computed the values of x. So the radius of convergence is basically the value we will extract from this expression because it's much more generalized and that has contains the much more value. So let us write 2x plus 1 mod less than 2. So here I can say that the radius of convergence. So the radius of convergence is radius of convergence. In this case, we represent by the r. We have the value 2x plus 1 mod that is less than 2. So basically, the radius of convergence is the x plus a mod less than r in general. So this x must be uh, independent of any coefficient that is other than 1. So this is written as a 2x. So this must be in terms of only x. So that must have the coefficient 1. So we will transform this 2x in the terms of x. So we just simply divide this expression by 2. So this gives us, just take as a definition. So we can write like 2x divided by 2. So this is the x plus 1 upon 2. So a is the center of the series mod less than 1. So this r is basically the radius of convergence. So here the radius of convergence is, or you just write like radius of convergence r is equal to 2. The radius of convergence is 2. Now we have computed the interval of convergence, radius of convergence, and let us look the last few parts, what we wanted to compute more. So in this case, so then identify the values of x of which the series converges. So we have already identified the endpoints for at the endpoints minus 3 by 2 and plus 1 by 2, the series is divergent. So and also we have to check on those endpoints either the series is absolutely convergent or conditionally convergent. So we have checked that at this point, let's back to the case 1. So whenever we applied that, there are no points where the series is absolutely convergent because if you put the mod, so that will give the same value. So there's no point to compute the absolute convergence. And the same goes for the conditional convergence for the both cases, case 1 and 2. So we can clearly say that uh, uh, interval of absolute convergence are the same as those of the simple interval of convergence. Minus 3 by 2 less than x less than 1 by 2. And the other one is uh, we have to check for what values of the conditional convergence. In this case 1 and case 2, there were no values to say that these two series for the case 1 and case 2 are conditional convergent. So we can say that there are there are no values, no values for which the series converges conditionally. Or in more general sense, you can also says that absolutely. So here in this question, we have summarized the four things. Interval of convergence. So first of all, we have extracted the values of the interval of convergence, like here, -3/2 to 1/2. Then we have checked on the endpoints, either on the endpoint series convergent or divergent. So we checked one by one. So we have found that the series is divergent on the endpoint, but it is convergent within the interval. So that was the first thing. The second thing was radius of convergence. So we took the generalized expression for the interval of convergence where 2x plus 1 mod less than 2, and the theory says that x plus a mod must be less than r. So x is the factor from the power series, that is variable. A is the a is the center of the series, and r is the radius. So we had the expression in this form we transform into the generalized form that is used to compute the radius of convergence. So we just divide the series by 2. So that is x plus 1/2 and less than 1. So the radius comes out to be 1. Sorry, I have done a one mistake. So this must be 1. This must be 1, not 2. I'm sorry, this is my fault. So I just realized this is 1 because I have said that the radius is equal to 1. Because here I have said radius is equal to 1. I think I did the typo mistake. So the radius r is equal to 1. And lastly, we have to check on those for what values the series is absolutely convergent or conditionally convergent. So we have checked that for the case 1 and 2, there are no values for which the series is conditionally convergent or absolutely convergent, because if you apply the absolute convergence, you will not find the different answer as we have computed in a normal series. So hence we can say that there is no point of absolute convergence and to the conditionally convergent. Here I have to conclude this tutorial session of the chapter 10. I think I have covered all the broad spectrum of these convergence of the series, starting from the integral test. Then I moved to the alternating series test, where I applied the three different conditions. And then later we moved to the conditional convergence. And then lastly, we have summarized all the things in the power series: interval of convergence, radius of convergence, interval of absolute convergence, and interval of conditional convergence. Thank you so much.